Hello friends, let's continue with the remaining part of this chapter, chapter 16. In the last lecture, we have discussed about the discrete case random variable kx. Today we'll discuss and start with the continuous random variable tx. Just a recap, tx is a continuous random variable which denotes the remaining future lifetime of a person currently aged x. As this is a continuous random variable, the probability has to be calculated only for a range, not for a particular point. That simplify means Tx is equal to 10 is a meaningless calculation of probability and its value will be simply 0 because Tx is a continuous random variable. So the probability has to be calculated only for a range. Say for example, when we say Tx is less than t, does that mean is that the person currently aged x dies before next t years, which we also call in actual notation as tqx. Similarly, if tx is more than t, that means the person currently aged x dies after t years or he survives till t years. Next t years after the current age x. So all this happens is because Tx is a continuous random variable for which the probability that Tx takes a specific value does not exist or its probability is 0. Again, reminder again, x is the current age and x is not the random variable. The continuous random variable here is Tx and not x and not x. X is a fixed number in the entire CM1 which denotes the current age of the policy holder. So then we can note down certain points. The first point to note here is the PDF of Tx. So we say like this ftxt, or sometimes we simply write as fxt in an abbreviated form. So this is what fxt or ftxt is, PDF for the continuous random variable Tx, and the formula for fxt PDF is tpx times mu x plus t. The proof of this is not in our syllabus, it's a part of CS2, so we just skip and learn it and use it in the exams. Next, let's continue with the present value random variable for the whole life assurance. So here we can say the present value of the benefits is v raised to power tx. So this is the the function of random variable Tx. Function of random variable Tx. We need to now find out the expected present value of v raised to Tx, and again the variance of the function v raised to Tx. So first let us find out the expected present value. So expected present value, expected v raised to Tx, is written in the actuarial notation as a bar x. And as you all know, for a continuous random variable, say we already discussed in CS1, expectation of gx is what? Integration of gx into fx into dx for the entire range of the values of x. Here, it expected of v raised to Tx. So a particular value of Tx is t, this is t, and this is the PDF. So basically this is integration 0 to infinity v raised to t ft dt, and ft dt is tpx times mu x plus t. So random variable function here is v raised to tx. Expected of this is equal to this into this. Exactly the same way, for variance of v raised to tx, it will be expectation of, let me write it here, variance of v raised to tx will be equal to expectation of the square of this. So v raised to tx whole square. A particular value of tx can be t, so v raised to t whole square minus expectation of v raised to the power tx whole square. And this can also be written as 2a bar x minus a bar x whole square. So what we have done, friends, is the expectation of v raised to power tx whole square. Variance will be the function square, expectation of that square minus expectation of the function whole square. We already discussed that this is calculated at the rate I dash, this part, and this part is calculated at the rate I. This I and this I dash. And we already seen in the last class, I dash is equal to I square plus 2I. So we got this answer, the whole life assurance, where the sum assured is paid immediately at the time of death. Earlier we had done was the sum assured was paid at the end of the policy year of the death. But here it's paid immediately on death. So this is a continuous function. Exactly the same way we can do it for term assurance as well. So F bar is term assurance. If the term of the term insurance is for n years, then if he dies before the n years, say this is n years, if he dies anytime here, he is being paid instantly at that time itself. And if he dies here, then nothing is being paid. So this term assurance is very similar to the earlier term assurance. The only thing is that here the payment of the benefit is done immediately at the time of death. And the earlier case, it was paid, in the discrete case, it was supposed to be paid at the end of the policy year of death. So again, the expected present value expectation of f bar b raised to t and ft dt, and then it is 0 to n because the other part will be 0. So n to infinity, the 0 into ft dt. So it's going to be 0. So we are only considering the one part. In actuarial notation, this is written as a bar x n 1. So bar indicates that the benefit is paid immediately at the time of death if it occurs before n years. And the variance of f bar will be exactly the same way, calculated at the rate of I dash minus, and the second part as usual, a bar x n 1 whole square. Then comes endowment assurance. So again, as usual, as in the past we have done, if the person dies before n years, he is being paid immediately at the time of death, or if he survives the n years, then he is paid at the time of maturity of the contract. So random variable is here h bar continuous is f bar plus g bar. G bar and G is the same thing because the benefit is paid at the maturity of the contract if the life survives till the maturity. So this is h bar, and as usual expectation of h bar will be simply expectation of f bar plus g. H bar in actual notation, expectation of h bar can be written in terms of a bar x n. There is no 1 over x, there is no 1 over n. So this will also be equal to a bar x n 1 plus a x n 1. In this case, when you put a bar or a is the same because the survival benefit is paid at the maturity of the contract. These are certain important formulas which are absolutely self-explanatory. A bar x is the whole life, this is for the term, and this for the deferred. So it's like this, the whole life, say 0 to infinity. It can be broken into two parts. One is this term insurance, the present value of it, and then the present value of the deferred part. So it is the deferred part. The expected present value here will be this part, and for the deferred part it is this. Claim acceleration approximation. In A bar X, the policyholder is being paid immediately, and AX, the policyholder is paid at the end of the policy year of death. So for simplicity approximation, we assume as if the person is getting paid here at the middle of the year. And then in this case, middle of the year, and in this case, he is being paid at the end of the year. And so A bar X will be approximately equal to 1 plus I raised to half into AX. This is the present value will be higher for this A bar X because this payment is done at the middle of the year, whereas AX payment is done at the end of that year. So A claim acceleration principle says the approximation will be 1 plus I raised to half multiplied with the AX. Exactly applying the same logic, this can be applied for conversion for discrete term assurance payment expected present value to expected present value of continuous term assurance payment. Let's go ahead. We can also use this approximation. Answer will be almost the same. The derivation etc. is not required for us. So we can use this formula as well. Another approximation. Both the formula will give you almost the same answer. You can use any one in the exam. The value of A40 is readily available in the formula book. And to find out A bar 40, either we integrate or we can use the approximation of the formula book. So once they have already said in the question to use the formula book, so we find out the value of A40 and then get its value by using claim approximation or acceleration principle. We already discussed what is select mortality. Its impact remains only for select duration. Only for, say, select duration is 2-3 years. So for 2-3 years, the mortality is little lower than the ultimate mortality. So only thing is that you just use the select mortality table. The columns from this select mortality from the table. So there's nothing great. The box has to be used. This is directly available in the formula book. And then we apply the claim acceleration principle. So that's the end of this chapter. You can try all these questions and come back to me if there is any doubt. That's all for today. Thank you.